Good morning, students. We're experiencing more of our cool weather in the morning, so hopefully you're enjoying that. I'm happy for it, and then we have a nice temperate afternoon. So, as I told some students yesterday during conference hours, this is our Florida weather without hopefully the number of hurricanes that they experience. There's always a price to pay for living in a beautiful tropical place, and it usually means tolerating Mother Nature. So I guess that's why most people just vacation in these really nice spots. What I want to do today is to complete our work with the triangles in chapter 6, that is cover the law of cosines. And then we want to talk about basic trig identities in the first section of chapter 7, which will actually be very simple. We already know all the identities we need to use in that particular section. And I'm going to share with you the cofunction identities, which I've alluded to at times. And also, I had some questions about the actual test. Your test number 3, I could cover through the law of sines, but I'll go ahead and stop with 6.4, and I'll just include the law of cosine, the law of sines on the next test, since that's related to what we do with the law of cosine. So that should be a little bit more ease for you, and it follows more of the syllabus. So again, that'll be hopefully a relief. Again, remember that you will write your problems out like you normally do, enter your responses on WebAssign, and then you're going to make a PDF scan of your work and submit that with Turnitin. And that's just easy to do. There are lots of apps, free apps that convert to PDF. The one I use is Adobe Scan, but that would require probably a trial period and payment. I have an account with Adobe. The PDF, the portable document file, is the academic standard, and we need to start using it. You know, unfortunately, you like to send me your work, and it's in all kinds of forms and a little bit hard to manipulate. The PDF, again, is the standard, and I would appreciate if you just scan your work and send that to me. Again, this is just a formality. I just want to see that you're working out the problems, and it, in most cases, will have no effect on the grade unless you just send in nothing. So basically, within the hour after you actually do your final submission from WebAssign, I'd like your PDF. So that gives you plenty of time to do that. So when you make your plans to test, make sure you have everything set up, how you're going to scan, and be able to take care of that. Again, I'm not going to be overly picky. If it takes you an hour and 5 minutes or 10 minutes, that's okay. But it should not take you beyond that. If anything, it should take you maybe 10 or 15 minutes. I'm sure you had to do this in other classes, so I'm not going to accept any, there'll be no exceptions with this. You will turn that in and be done with it. Again, make sure as we get towards the final part of the semester that you adhere to due dates. It's important as a college student that you adhere to these things. Our grades must mean something, and we must show responsibility in a college class. And I know maybe I'm a little bit more significant in that area than maybe other professors, but as a math professor teaching STEM mathematics, I've got to train you to be excellent at what you do. And that's what the goal is. So just keep that in mind. Remember, when it's over, it's over. And you can celebrate and prop your feet up and at least know that you'll have a little bit of break, unless you're just going to plunge into the 3-week mini. If you've got that set up, good for you. If not, it'll be a nice break. Okay, so what I want to do is go ahead and share the screen, and we're going to talk about the law of cosines. Now, the law of cosines is really just an extension of what we've been doing. Let me move Professor Ron over a little bit, just so that we can cover the cases of solving a triangle that the law of sines did not allow us to do. And so, for instance, let me just write this in red. We have 2 other cases, the side, 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 and the side, angle, side. And these cases required another approach. So I'll just say this, the present theorem covers these cases. And be sure, ladies and gentlemen, to do your work exactly. Write out everything exactly. And don't round as, like, if WebAssign says round to 1 decimal, that's fine. That's the final answer. But don't use a rounded number in your calculations. That just basically obliterates the correctness of your work. It's like, okay, square root of 2 is your answer. And so, oh, well, I'm just going to use 1.4 in all my computations. That's incorrect. That is incorrect. So when you are approximate on the last step. Do not use rounded numbers in your computations. Again, I don't think this is exactly your fault. It maybe is just being slack in other classes and not paying attention to what you're doing. So let's always make sure we either run out lots of decimals or we do exact calculations to preserve the mathematics. Now, let's go ahead and state this theorem. We're just going to start with a generic triangle. Let me get these papers right. So we'll have our theorem. And let's just consider a generic triangle. We'll do one case here. Consider a generic triangle. Then there's a relationship between the lengths of the sides and the angles, and it comes in 3 forms. Sometimes this is called the generalized Pythagorean theorem. So you're going to see the Pythagorean theorem in the formulas. So the first form will look like this: c squared equals a squared plus b squared, which reminds you of the Pythagorean theorem, but then there's a correction: 2ab cosine of the angle C. Now, of course, this is like the area formula for the triangle. You can just pick on another pair of sides or threes and just move things around, just permute the a, b, and the c. And so then we could do maybe a b squared equals a squared plus c squared minus 2ac, then cosine of the angle B. So what you're seeing here, it's kind of easy to remember. The letters you put here go in the product, and then the angle here corresponds to the angle opposite B. So this generic triangle labeling is really nice, and it makes it easy to remember these. And now let's just pick on A. So we'll have b squared plus c squared. Just like the law of cosines, this is easy to remember. So 2bc cosine A. So just like the law of sines, you'll use a form that corresponds to the labeling, but all of these are the same. There's nothing extra by writing all of these. I'm not trying to say there are 3 results. They're all equivalent. So it just really depends on how you label things. So what I wanted to do was just basically show you why this is true for the obtuse triangle. I keep forgetting all the time. I always use my mouse on my computer, and I have a touch screen, and it's weird. You buy all these nice features that you never use. And so if my mouse went out, I'd still be fine, but I think I would still go out and get a new one. Okay, so what I want to do here is just draw an obtuse triangle. But first, I'm going to set up a very simple coordinate system where I'm going to place one of the vertices of the triangle at the origin to make it simple, just like you're doing in a science class. So here's our x-axis, and here's the y-axis. So it doesn't matter how you label this. I'm going to put one vertex here, and it's going to be obtuse, so I want this to be an angle that's in the second quadrant. And then just take a point here for the third side and connect this. So what I'm going to do in this case, yes, did someone say something? Okay, maybe that's just feedback. So here is A, vertex A, and then what we're going to have here, so this side of opposite will be an A, and then I'm going to put B here, but we're going to hold off on what its coordinates are. We're going to have to work on those. And then for C, notice B angle, and then over here we have side B, and here vertex C will just be what? B comma 0. So this is where we use the lazy nature of notation in mathematics. C has all kinds of attributes. It denotes the angle, it denotes that point, and then by the point we put the actual X and Y coordinates. Here we have A, again, which is the point, and the angle, and the label of the X and Y coordinates here, which are the origin. So you can see when you're actually trying to do a coordinatization, I can't even say that, coordinatize, I'll just do the verb, coordinatize a geometric object, it's very nice when you can choose one of the actual points to be the origin, because that simplifies things. Now we're thinking, okay, we have this obtuse angle. So the other case would be where this would just be an acute triangle. And you can work on that because it'll be just like this, but actually a lot easier. So now what we want to do is we want to use our reference angle, which is Professor Ron's favorite. If you understand the reference angle and the reference number, then you have mastered the unit circle. So let's drop the perpendicular here. Get some ink going. And so now notice this is an angle A, but this angle here is just the supplement. This will just be pi, or 180 degrees minus A. Notice the angle A is in the second quadrant, and this is just the reference angle here by definition. So we can do some trigonometry here to figure out these coordinates. So notice here, when we look at all of this, we're thinking, well, let's just give these some labels. For right now, let's just call this Y, because it's going to be the Y coordinate of B. And let's just call this X, because it's going to be the X coordinate of the point B. Labels, you can call it anything you want. You could call this OPP for opposite or ADG for adjacent. It doesn't matter. How you choose to label is completely up to you, and you're in charge, so you do what you want. So now we can see, for instance, at this point, let's just go ahead and do the sign. So we have sine. So now let me just observe. We like that word. We use this in math all the time. Observe that pi minus A is just the reference angle for A. Okay, that's just the definition. This is an angle in the second quadrant. And so its reference angle is pi minus the angle that we've done a million times. So now we see, okay, well, sine, in this case, of A hat or A bar, now that's going to be equal to, in this case, sine of A, because in this case, in the second quadrant, the sign is positive. So this is also sine of A. Again, in the second quadrant, the sign, the Y is positive. And then what is this? Y, and this right here, let me go ahead and label it, that's C, that's the side opposite C. So this will be opposite, which is Y over C. If and only if. Very simple calculations, but very important calculations. Y is equal to C times sine A. Okay, So we'll just put a little box around that because we're going to use that, and we're going to move it up here once we find the x coordinate. Now we can do the cosine. So this is just kind of the preliminary computation. The cosine, we have the reference number. Of course, now we have to use the fact that the cosine is, in this particular case, negative in the second quadrant. So we have to transfer the negative sign. So this will be the negative of cosine of A. So we're kind of doing this in reverse, all right? But it's the same thing. We're just moving the negative as we would have to do if we were doing it in the opposite direction. And this will be adjacent over hypotenuse. So this is x over c. So if and only if x equals the additive inverse of c times cosine of A. So again, when we're working with inverse trig functions, we have to remember how they're defined in order to do the arithmetic. Again, when we're working with angles, we have to remember the definitions for reference angles or reference numbers. They're the same. Ignoring this is ignoring the foundation of trigonometry. And so I teach you the same way every time I do a problem. I focus on the arithmetic. If you ignore the arithmetic, then you're making it up. There's no reason why you should not understand trig when you get to calculus if you've taken my class. So it's on you to make sure that you have mastered this. These are foundational topics. So please, please understand this. And don't rely on a fancy calculator to do this. Use your Google calculator for approximations, but you do this work by hand. Now let's go up here. Now I always have to preach a little bit, but you know me by now. So this will be C, the opposite of C, cosine A, and then C sine A. So we've got the coordinates now. So what we're seeing here is that now we've got this big triangle. We've got all the points here that we need, and we've got this big triangle, which is going to allow us to use the Pythagorean theorem. So here is the large triangle. Now notice, so use Pythagorean theorem. So we're using the Pythagorean theorem to prove a generalization of it. That's okay, that's not circular reasoning. I mean, this is a right triangle here, so we can use it. So it's not like we, are assuming something in the proof, which is part of the conclusion. So we're good. So now notice we have a squared. So I guess we're going to prove this one since this is the way I've set it up. So here's the hypotenuse. So that's a squared equals. And so now we've got this side right here. So we computed that. It's right here. We're going to square C sine A. So C sine A squared plus, now we need the other side, which again will be B plus the x coordinate. So we have B, this distance here, plus the x coordinate. So we have B minus cosine A quantity squared. So the idea here is once you set up the actual coordinatization. I can't say it this morning. I'm putting in an extra syllable. These Invisalign really make it hard to do, but I'm trying. Maybe by the end of the lecture, I'll be able to say it. A little bit of humor there. Okay, so now let's just expand this, and then what we should be able to show is that we get this equation here. So a squared equals c squared sine squared a. Remember, our lazy notation for sine of a quantity squared is this. Just remember that this is our lazy notation. Remember, every time, and you need to know this, we use it all the time. Sine squared of a, or just sine squared, is just sine of a quantity squared. So to avoid having to write this, we choose this. And again, remember that. Now, of course, if we're squaring the argument, this is something completely different. This is sine of a squared, and that's completely different. This does not equal. These are not the same. These are clearly different. So don't make that mistake. If I'm going to take the sine of a squared, that's fine. But when I'm taking sine squared of a, that means sine of a quantity squared. So don't confuse this, please. I'm very careful with my notation, so make sure you get that right. Now, let's square this, square the binomial. How simple, right? We have b squared, and then we take the product and hit it with a -2. So minus 2. Oh, and then, of course, over here, I left out my c. Let me give a little more room for the c here. Need the c, then the cosine. The math always tells you if you've got a typo. So now we get the minus 2bc cosine A. So I need that c there. And then square the last term plus c squared cosine squared A, just like we have here. And now you're thinking all of it's good. Notice here, this is this term right here. So that's a check. So this is what, c squared, and we've got a sine squared and a cosine squared. Plus b squared minus, so that's a check too. No, don't have to do anything to that, 2bc cosine A. And then of course, this is just where it all began, the unit circle, the standard fundamental identity. So we get a squared, and we'll write this in order, b squared plus c squared times 1, which is c squared, minus 2bc cosine A. So the proof here is a little bit more complicated than the sine, law of sines, but it's very straightforward in the sense that we use the arithmetic of the unit circle and the right triangle. So we combine the two interpretations. So I like you to see this because this kind of reminds you of doing a word problem. If you were doing a word problem, you would need to coordinatize. And so we're seeing that the coordinatization, I got it, no, Professor Ron finally got it, is the way to approach these triangle problems. So again, we combine algebra and analytic geometry. Okay, so the analytic part of the geometry is coordinatizing everything so we know what the x's and the y's are for each point. So that's what we'll do more of when we do the conic sections. Now, so that's good. We're good with that. Now, here, let me organize here. Let me move this over here. Now what I want to do is take this law of cosines, and we're going to do some examples. I want to share with you a result that we get by using the law of cosines, which is a more generalized form of the area of a triangle. So for instance, this is going to be, and you may have heard about this in your high school class, or if you didn't, it doesn't matter. I started at the beginning. This is going to be called Heron's formula. So all of these Greeks, they came up with all of this stuff, you know, way before we had all this fancy notation. And so they were really smart people doing math with little or no notation that was standardized. So what we want to do is consider a generic triangle. So say we just had that, we'll just do the simple one. And so we'll have A and B and C. We'll just look at that one. This is a form, and then of course I'm focusing on this because of course this would be A and angle B, and that would be C. But this would be the generic triangle if we were thinking about area. So this would be basically formula for triangle area. Now you're thinking, we have that formula from sines. You know, when we're using the sine of theta when we've got the included angle like we have here. And we're thinking, well, do we need another one? Well, the beauty of this formula is that when we get something, it will only include parameters that are the lengths of the sides. So if you know the side dimensions of a triangle, then you can also compute the area, which is kind of like 1/2 base times height, but the height's not really a side. It's constructed. So the thing is that this is like, I don't believe it. I can actually get the area of a triangle by using the lengths of the sides. That's what Heron determined. So what we're going to do is we're going to let A equal area of triangle. This is another good algebra exercise that I want you to see. It's like doing identities, and I need to get you back into doing algebra. So in this case, what we're going to do is say, okay, let's start with the formula that we learned a couple of lectures ago with the sine of the included angle times AB. But we're going to start with the square just to simplify the notation and the algebra. So A squared will now be 1/2 AB sine C quantity squared. So that's our formula, and you're thinking, okay, so magically this is supposed to transform into something else. Now, to help us out, because you're thinking, there's not a whole lot of given here, Professor Ron, you just start with a triangle. So we need a new object. It's called the semi-perimeter. So let's define that. We're going to say semi-perimeter. And we're going to call, now I'm sorry, this is a bad letter. You know, we use S for arc length, but we're just going to use lowercase s for semi-perimeter. Again, always remember the context. This will not be the arc length. So if you're thinking about a triangle and area, then this S will be the semi-perimeter. So if you want to call it something else, that's fine. But this will be basically, you add the lengths of the sides, and the semi part means you divide by 2. So this construction will be in our formula. We're going to basically force this upon the formula. And so now when we actually state our theorem, it will be a function of the semi-perimeter in A, B, and C. So this is new and maybe a little bit odd, but that's okay. That's what we have to do. Mathematicians get together and come up with interesting ideas and develop new objects which make our understanding of mathematics even better. So let's move forward with this. So now you're thinking at the very end, we'll take a square root. So that'll be one thing that'll be obvious. So let's square everything. So this is 1/4 A squared B squared. Well, that's easy. And then we now get to use our notation again because we're lazy. Remember, the square of sine C we write as sine squared C, just like that. Now you're thinking, what's the first thing we can do? This is going to help us with identities. So we're going to rewrite this with 1 minus cosine squared. So first, we'll say 1/4 A squared B squared. And then we'll use the fundamental identity, which is 1 minus cosine squared. Now, again, this is just all basic algebra. So first, we use the formula for the area of the triangle using what we just learned a couple of lectures ago. We square it out, then we use the fundamental identity. Now, we're just going to apply some basic algebra to this. We're going to write this as a difference of two squares factored, because that's what it is. So 1/4 A squared B squared. So we have 1 minus cosine C, and then 1 plus cosine C. Okay? So that's the key right here. Now we see that this is really basically a corollary. Heron's formula is a corollary of the law of cosines. at least in how we're proving it. Now, Heron may have come about this in a completely different way, and you all could do some research and figure out how he actually proved it. But the idea is at this point, we're going to use the theorem law of cosines to push this problem forward. So this will actually be a corollary or a side product of the law of cosines. So now let's go up here and remind ourselves where we got this formula. And this is what's important. Notice when we've got the side angle side, the C is over here. So do this in blue. So recall C squared equals A squared plus B squared minus 2AB cosine C, which is what we need here. And so we're just going to solve for C. So now what I want you to do is take this over here and take the C squared over. So this is going to be 2AB cosine C equals A squared plus B squared minus C squared. That's just simple transposition. And now divide by 2AB cosine C equals A squared plus B squared minus C squared divided by 2AB. Now we have you're starting to see, oh, I get it now, because now we just have A's, B's, and C's when we replace cosine C, and everything is in terms of A, B, and C, and then we'll somehow find a way to move this into the formula. So now we're basically writing an equation that only involves the lengths of the sides. So again, this is a corollary of the law of cosine. So let's replace it. So we have 1/4 A squared B squared. So now just go ahead and substitute. So we're going to have 1 minus A squared plus B squared minus C squared divided by 2AB. And then we have 1 plus A squared plus B squared minus C squared divided by 2AB. Now what we want to do is get some common denominators, and let me check the focus. So let's do a common denominator. So now it's just algebra. We just use our algebra skills. So now the 2AB, and then we're going to get a nice perfect square, a binomial. So these 2ABs are going to go away because of the ABs here and the 4. So we're going to get a 16, and the A squared B squared will be history. So we have 2AB here. So this is 2AB minus, so now distribute the minus sign here, minus A squared minus B squared minus a negative plus C squared, right there. Distribution law. 2AB, so we have 2AB, now plus, that's simple, just a plus sign. We have what? A squared plus B squared minus C squared. Now, notice, this is just a perfect square here. This is minus A minus B quantity squared, because we need the negatives in front of the A squared and B squared, so we need a minus out front. And this one is just A plus B quantity squared. So it's like the difference of squares is what's making this problem work. So that's why we need this squared term. Otherwise, we'd have radicals all over the place and we would lose our minds. So squaring things, it's like squaring distances when you do calculus problems. It's the equivalent problem, but in more user-friendly form. Now notice everyone, AB, that's A squared, B squared, absorb. But then these 2's will join here and we'll get 4 times 4, which is 16. So notice the AB in each here absorb with the A squared, B squared here. So let's do that. So we're gonna have 1 over 16. Again, 4 times 2 is 16. The AB's absorb here. And then we can put in our difference of squares. So write the c squared first, minus a minus b quantity squared. And then here, it doesn't matter. We'll just write the positive first, a plus b quantity squared minus c squared. These problems are really good to do because the algebra is very simple, but you never learn any math if you don't see them. Your skill set never improves if you don't work through some of these. You just keep doing the same thing over and over and wonder why you don't get any better. So at this point, you're thinking, okay, is this where we stop? Well, no, we want to get some simple linear terms here. So we're going to rewrite this with the difference of squares. Factor it like we did right up here. Do the same thing. So this is going to give us 1 over 16. So now we're going to do c minus a minus b times c plus a minus b. So remember, when we do the difference of two squares, we do c minus this term, a minus b, and then we do c plus this term. Do the same here, just using the formula. So this will be the a plus b minus c. And then we have a plus b plus c. Okay? So now we're thinking, oh, that looks like part of the semi-perimeter. So we're getting where we need to be now. So just simple factoring. So now we've got 1 over 16. Let's clean all of these things up. So minus minus, this will be a b plus c minus an a. B plus c minus the a. The a survives with the minus, but the minus minus gives us a plus b. Do these in alphabetical order. It's easier to see. A plus c minus b. Well, that's already done right there. A plus b minus c. And then that's just a plus b plus c. Now you're thinking, we're going to distribute this 16. It's 4 sets of 2, 2 times 2 times 2 times 2. But before we do that, we need to rewrite these in a way so that we can introduce semi-perimeter in all of these factors. It's already there. So we're going to do a little algebra trick. We're going to add and subtract a. So we get 1 over 16, all very simple algebra, a plus b plus c minus 2a. So here I added a and subtracted a right there. Do the same here, add and subtract b. A plus b plus c minus 2b. Here, add and subtract c. A plus b plus c minus 2c. And then, of course, that's fine. We just leave it alone. So basically, I added 0 to each term. So that doesn't change it, does it? We're rewriting it. So now when we divide by 2, divide here, we got 4 copies of 2. Put one here, put one here, put one here and here. But then, of course, that'll make that into a minus a, and then we get semi-perimeter for free. So now distribute the 4 2's. So we get a plus b plus c over 2 minus a. We get a plus b plus c over 2 minus b. And we get a plus b plus c over 2. And again, the 2's absorb minus c. And this is just the lone semi-perimeter. Just divide by 2. So there's S minus A, S minus B, S minus C, if you can believe it. So now let's just finish it. So this, and we'll just, let's just make it look real user friendly. Let's move the S all the way up to the front. So we have S minus A, S minus B, S minus C. Now, when you see this formula, it's like, well, I can remember this, that's easy. S is just that. So now at this point, we take the positive square root because the area is positive. So take positive square root. We do a lot of square rooting with the trig because of the unit circle. So this implies that A is just the square root of S times S minus A, S minus B, S minus C. So now when you have a triangle and you know all the lengths of the sides, which is sometimes the case, then there's the formula for the area. So basically you compute the semi-perimeter and then just form this product and square root it. Now, of course, if you try to make up a triangle that can exist, this formula won't work. You'll get negative factors. The A will exceed the semi-perimeter, or the B or the C. If you just try to indiscriminately make up a triangle, it may not work. It's like the law of sines and the law of cosines and Heron's formula keep everything honest. You can't just indiscriminately, oh, let's have this angle, let's have this side. If the mathematics doesn't support it, the triangle does not exist. So this is a really good way to check models when you're working in physics or you're working in engineering. Maybe your model's not possible. It's like, well, you need these dimensions, but you can't construct that triangle. You got to build it. So we've seen here that the language of mathematics, the language of mathematics provides the language for physics and engineering and computer science. So when people say that physics is the mother of all science, it's really mathematics, because the mathematics is the key to understanding everything. You know, if you're an astronomer, you need mathematics. If you're a physicist, you need mathematics. If you're a chemist, you need mathematics. If you're an engineer, you need mathematics. If you're a computer scientist, you need mathematics. I can go on forever. Heck, if you're a financial expert, you need mathematics. Mathematics drives the STEM culture. So if you want to be an engineer, you need this. This is not an optional thing. It's like if you want to be a music major, you've got to practice. If you want to be a STEM major, you've got to do math. So now we have a formula that just beckons us to use it. It's kind of like, wow, we've got this nice device here that will allow us to solve neat problems. So let's do some examples. So yeah, know how to do this. Teach your friends this proof. This is easy to do. If you work this problem 3 or 4 times, practicing the algebra, you will master it. And share this with your friends, okay? If you teach it to someone, you'll master it. And of course, Heron probably did not approach his theorem this way. Maybe he just dreamed it up and boom, it worked. Who knows? Maybe you all can look into that. Do some math history. Math history is good. Now, what we want to do is look at an example. We'll look at a Heron's formula example first, then we'll go back and look at the law of cosines. So now here's an example. It's really easy, but we can do it now. So we've got 2 isosceles triangles. WebAssign gives you a silly problem, but I like it. Oh, let me start again with the side of the triangle. So what they do is they just juxtapose 2 isosceles triangles. So it's kind of a simple idea here, but what we have here, we have 3, 3, 3. So all of these sides are labeled, and this is a 1, and this is a 1. So we've got the first triangle, which has side lengths 1, 3, and 3, and the second one the same, and they're both isosceles. So they have the same area. I mean, Heron's formula says they have the same area. And then, of course, in Euclidean geometry, they would have the same area, but that would require another proof. So what we want to do is compute area of the object. And when I say compute the area, ladies and gentlemen, I mean the area that's enclosed here by the two triangles. So for instance, all we need is the area of one triangle. So let's just call this 1 and 2, and we'll say the area equals 2 times the area of, pick a triangle, just say triangle 1. Triangle number 1. Okay, so since these again are congruent, so to speak, they have the same area. So now let's just figure out the area, use Heron's formula. So now and this is where you can be completely spontaneous. It doesn't matter. We'll just say that A equals 3. We'll say B equals 3 and C equals 1. It doesn't matter. It doesn't matter. I mean, again, you can label these however you like. And now let's compute the semi-perimeter. This will be A plus B plus C divided by 2. So we get 3 plus 3 plus 1 divided by 2, which is 7/2. Now, if you like, ladies and gentlemen, you can go ahead and do all of the preliminary calculations and then put them into the square root, kind of like we're doing the discriminant for the quadratic formula. Don't worry about it. It probably makes your computations a little bit more streamlined. So now we've got S. So we'll do S minus A. And so we have, in this particular case, 7/2, and A is 3, so let's write that as 6/2, so we get 1/2. And then S, well, we know what that is, just write it down again, 7/2 minus 6/2, which is 1/2. And then, of course, S minus C will be 7/2 minus 1, which is 2/2, which is 5/2. Now, when you look at this, you're thinking, okay, well, I've got all the particulars here, and I can use Heron's formula. So at this point, use Heron's formula. Well, obviously, we're thinking about using this. So we see area. Let's just go ahead and do the area squared. This will be S times S minus A times S minus B times S minus C. So let's fill it all in. We get what? 7/2 times 1/2 times 1/2 times 5/2. So now if you look at that, that's just 4 times 4. So that's a 4 squared, you know, in this particular case. Now, let me just say this. 7 times the 5 is 35. So let's write it this way. So it's easy to square root. So now, if and only if, well, and again, this is just the area of one of the triangles. Let me just write it this way. We'll call this A1 for area of first triangle squared. So A1 will be what? The square root of 35 divided by 4. Therefore, the area of the object equals 2 times A1, area of triangle 1, which I'm now calling A1, which will be 2 times the square root of 35 over 4, which is the square root of 35 divided by 2. So when you look at these problems, again, work them out Exactly. WebAssign may say, approximate your answer with 2 decimals, okay? For instance, you have plenty of flexibility when you do mathematics. For instance, if you need an exact answer and you know the exact answer is 1/4, you could also write 0.25. A decimal is not an approximation if it's equivalent to the exact response. And again, some of you don't understand that. And again, I think it just might be poor training. So just remember, if you would rather type a decimal equivalent to a fraction, no problem. It's equivalent, okay? It's just that in this case, the square root of 35 is irrational, okay? And so this is the exact answer. And that's what you always want to strive to get. And then if WebAssign requests an approximation, you can use your Google calculator. So again, let's make sure that we keep our mathematics correct so that when we do approximations, we've got exact numbers to use for that. Or if you carrying decimals in approximations, make sure you carry out plenty of decimals so that the rounding does not work against you. One or the other must be what you put into the thought process when you do these problems, okay? And technology, I think, has forced us to think that the approximation is better than the exact, and that is patently false. Just nonsense, basically. Now, let's look at an example using the law of cosines. And what I want to do is just say, okay, let's try to solve a triangle where we don't have the hypotheses of the law of sines, but we do have the hypotheses of the law of cosines. So now we've got these new tricks. Basically, the first trick is the law of cosines, which gives us Heron's formula, which now is like, man, I've got this great formula to find areas just using the side lengths. So let's just do a simple example of solving a triangle. And here's what we have. WebAssign gives us angle C is 120 degrees. We have side A is 24 and side B is 20. So if you like, you can just draw a little picture of this. Sometimes drawing a little picture makes it look a little bit more believable. So we have something like this. So we've got our 120 degrees. This is angle C. And of course, this is C. And here we'll label A and B. And we have what, 24 and we have 20. So basically, when we look at this, we have side angle side. So this is side angle side. And we know that this generates one triangle. These hypotheses are sufficient for one triangle. We know that side angle is that ambiguous case. Clearly, we could always get no triangle if the hypotheses don't make any sense. That's always on the table. But we look at these as one triangle when it exists. But when the ambiguous case, we're like, okay, we could have one triangle or two triangles if we use Professor Ron's lemma with the sine equation. Whereas we could look into the second quadrant and get another angle, and then the angle sums make sense. But if the angle sums don't make sense, then of course the ambiguous case only gives you one triangle. Okay, so that's good. So here we say one triangle. And so we want to use law of cosines. So now when we look at this, we're thinking, okay, well, we've got the C here. So we know C squared equals A squared plus B squared. I'll just write this out since it's a little bit more complicated. Minus 2AB cosine of C. And we need C squared, or we need C or C squared, so we're good. So let's fill it in. So we have C squared equals, in this case, 24 squared plus 20 squared minus 2 times 24 times a 20. And then we've got a cosine of 120 degrees. Now, when you think about this and you think about what we're doing, what's interesting about this is that we're going to start with the square and then try to reduce it. But this is an angle that doesn't require the Google approximation. Notice, in this case, theta hat is just 60 degrees. So this implies cosine of 120 degrees, since this is in the second quadrant, is the negative of cosine of 60 degrees, which is negative 1/2. So that's where we use our arithmetic of the unit circle. So what do we get? We get 24 squared plus 20 squared. Now notice this is a negative 1/2 in this case, so we get a plus, so minus minus, so we get plus. We have the 2 times the 1/2, that just absorbs, and we have 24 times the 20. Now what we can do in this particular case is just do some simple factorization to see what we get. Now notice again, let me just say this. This is important here. If you had to approximate, that's fine. You don't get as pretty a numbers. But notice we have the 2 negatives, so they absorb, and that just gives us a 1 here. So now let's factor. Here we can take out say a 24 out of these two. So just underline these two. So we have a 24 times a 24 plus a 20 plus 20 squared. So now if we look at this, we're thinking, okay, how can we reduce some of this to make it even more user-friendly? Notice here that we've got 4s here, and we can rewrite some of this. So let's just think about this. So this is a 4 times a 6. And here we get a 44. Plus, and here we've got 2 4s in here. So we've got a 4 times a 5, 4 times a 5, just kind of reducing this with symbolic arithmetic. So now if we look at this, we've got a 4 here, a 4 here, and then we've got a 4 in here and a 4 here. So we've got a 4 squared. So that leaves a 6 times an 11 plus a 5 times a 5, which is a 25. Now, the sad part about this is that there's nothing left here. This is 5 and 5, that's 6 and 11. They're relatively prime. So we get 4 squared, and we get a 66 plus a 25. And that'll give us a 1, a 91. So 4 squared times a 91. And that's not completely crazy, but at least it's a decent number that we can square root. So now this implies take positive square roots. I just want us to get some practice in using the symbolic computation, which we always do, but we haven't had to do a lot of it lately. So C, the square root of 4 squared is 4 square root 91. So that's exact. So that's C right there. Now, of course, if WebAssign says approximate it, we can easily do it. But we want to keep our answers exact so that we can, do good computations. So now when we look here, we've got all these angles working in our supporting us, so to speak. So now we've got this. We'll just kind of mark that with red because it's new. Now, if you like, and this is your choice, when we look at this particular setup here, we want to be able to find some new angles. So notice we've got the C in the opposite side. So maybe we could find B using the law of sines. So now use law of sines because it's easy. So we can do sine, I'll write it down, sine of C over C. And if you like, just pick on B, angle B. So that'll be sine of B divided by 20. And so now we can solve for sine of B just by cross multiplication. So sine of B will be 20 times sine of this case, let's go ahead and write it in, sine of 120 degrees. Now, of course, I should have just written a B there. Sorry, that's just a B. Keep it abstract. So now when I multiply here, I get the B, and that's 20. And then we got sine of 120 degrees. And then we have C right here, which is 4 times the square root of 91. Now, of course, the sine of 120 degrees, we just can go over here. Remember, the theta hat is 60. So sine of 120 degrees equals sine of 60 degrees, because again, in the second quadrant, the sign is positive, and this is square root 3 over 2. So we have all these exactly. So this is 20 times the square root of 3 divided by 2, 4 times the square root of 91. And of course, the 2 absorbs here. So we've got, well, in this case, we've got 10 root 3, 4 square root 91. And then, of course, this will go one more step. If we want to go ahead and reduce this, that'll be 5 halves. So we can write this as 5 halves, and then put this under one umbrella, 3 over 91 to the 1/2. So again, the square root of 3 over the square root of 9 is just the square root of 3 over, 91 is just the square root of 3 over 91, written more conveniently using the laws of exponents. Now we're thinking, okay, well, what is this going to do? Notice this is a 120-degree angle, and what's left is just 60 degrees, okay? So this, the law of sines is going to give us the acute angle from the inverse sine. So we don't have to make any adjustments here. This is going to give us directly what we want for B, knowing the inverse sine function. So equivalently, B is just the inverse sine of this guy. So we have 5 halves, 3 over 91 to the 1/2. So you can just kind of put that in brackets like that. And this is where we would, this is exact, but we'll use our Google calculator. So this is exact. And then we'll be good. Then we can get angle A and we'll be done. And we'll use our exact calculation with our Google calculator to preserve the decimals so we don't have to, you know, ruin our calculation. So now let's go to Google. Now I'm going to have to find this. It always runs around on me. So let me just say, let me move this over here. Let me get rid of that. I don't need that. So here, let's see, let me move this around a little bit. There we go. So we have our Google calculator. So now remember, we want degrees. So go over here and make sure the degree is highlighted. We want the Google to do our conversion just to give us a little less to worry about. So now we'll have inverse sine. So inverse sine, so we get arc sine. Remember, that's the equivalent expression for inverse sine. And then we're going to do, in this case, 5 divided by 2, close, times the square root of 3 divided by 91. So we're going to do square root, and we're going to have 3 divided by 91. Close, and then close the arc sine. And this will give us 26.9955. and then you can say et cetera. And that's in the first quadrant. That's exactly what we need. Now, I'm just going to stay on this screen, and I want you to, your notes to write angle A will simply be 180 degrees minus 120 plus the inverse sine of 5/2 times 3/91 square root. That's exact. Now here's what you can do. We have this beautiful approximation here that's run out to like 10 decimals. Use that in your calculation. So what you can do in this particular case is add 120 degrees and then just subtract this from 180 and you'll get the negative of the angle. So this will give us 33.00449, etc. Now, this is what I'm talking about, doing exact calculation. And this is important, otherwise you will ruin your mathematics. So here, if we want to use this in this calculation, then we do the exact here. So instead of, and to keep from having to write, to actually input this again, save this calculation with an excellent approximation. And then you can actually write this exactly and use the number that Google gave you that's run out to a sufficient number of decimal places. That's called exact computation. Do not under any circumstances round this to what WebAssign asks you to do and then use it in another calculation. That's what I'm talking about. That is poor technique and it makes your work incorrect. So here, to save having to type this in again, you can save this calculation and use it here. That's what I mean by exact computation. And now WebAssign says in this particular case, they say round to 1 decimal. So in the case of D, we would have 26, well, the 6 has gone away, 27.0, because the 9 rounds up. So this would be our approximation for B. And then this to 1 decimal would be 33.0 degrees. And that's our approximation for A. So this is what I mean, ladies and gentlemen. You know what I'm talking about, and that is sloppy, incorrect mathematics. And if you do this in your science classes, then shame on you, because that is just incorrect. And I do all of my calculations exactly. So I don't know why you are possessed to do that sometimes. Please don't do it. Use the exact computation and keep any numbers that are given in a wonderful approximation to use in a later calculation so you don't have to re-enter it here. But everything needs to be done exactly. If not, your calculations are ruined. So please don't do that. Don't make that mistake. I have trained you better and I want you to do good work. Don't make it up. The math will always assist you, but you can't make it up. Now, so that's the law of cosines and Heron's formula. Now what we want to do is just do a few identities. And these are easy. I saved this for last because the identities are simple because we're just using what we already know. So when we do identities, basically we can do some simplifications if you like, but the identity is just what? An equation that is true for all values of the variables for which it is defined. So what Dr. Stewart does is he says, okay, here are all the types of identities that we've had so far, which I don't need to repeat, but I'm just going to remind you, an identity is an equation, that is true for all values of the variables, maybe there's one variable or two or more, all values of the variables, just like the logarithms, just like the laws of exponents, values of the variables for which it is defined. So we live for identities. Cosine squared plus sine squared equals 1. 1 plus tangent squared equals secant squared. 1 plus cotangent squared equals cosecant squared. Those are the Pythagorean identities, which basically are the generator of everything we do. And so, you know, we know that secant is 1 over cosine by definition. Okay, we know that cotangent is 1 over tangent. We know that tangent is sine over cosine. So just the basic identities that we live to do, you know, that we have to have in our back pocket to do basic computations. So one set of identities that I want to share with you are called the cofunction identities, which can actually be justified using a right triangle, and you should do that. But I just want to state them for you. These are called the cofunction identities. So these are the only ones that we add to the lists. And you use this when you did a proof with the inverse sine back in 6.4. The cofunction identities have pairs. So we'll say you can use 90 degrees or pi over 2 radians. Cosine of pi over 2, these are just using complementary angles in a right triangle, minus x equals sine of x. And then the companion formula is sine, in this case, of pi over 2 minus x equals cosine x. Now, what I mean by this and what I'm trying to say here is that when you think of the right triangles and you flip to the other acute angle, then the sines and the cosines flip. So for instance, if you look at a very simple triangle here, and we say we've got our right triangle here, and we have x here, and then we have pi over 2 minus x, just using radian measure. You can use degree measure, it's the same. And so for x, we might want to think of this as, I don't know, you can use anything you want. Let's just say hypotenuse. And for x, we'll say adjacent. And the opposite, OPP. So now, if I do sine of x equals opposite over adjacent, right? Opposite over adjacent. But now cosine of pi over 2 minus x will just be adjacent over hypotenuse. But again, here the adjacent is the opposite for this angle. So it just flips, but you get the same thing. Oh, and sorry, that's a hypotenuse. So we get the same thing just using right triangle. So this is an easy proof using the concept of right triangle. So this is where we say sine, cosine, cofunctions. When we go to the complementary angle, sine and cosine are the same. That is, when we say the sine of x, that's the same as the cosine of the complementary angle, and vice versa here. So using the right triangles makes this very simple, which we can impose on the unit circle. So these we already really knew, but we didn't have the best way to get to them until we had this right triangle. Now when we have addition and subtraction formulas, these proofs will be even easier, but we don't have those yet. Those will come in the next section. So for right now, we have an easy way to basically prove these ideas. Now we can do the same for tangent, cotangent, and secant and cosecant. So let's write these down. So we have secant of pi over 2 minus x, same proof. You can use your triangle to validate that. Will be cosecant of x. and then cosecant of pi over 2 minus x is secant of x. 3, same with tangent and cotangent. Tangent of pi over 2 minus x equals cotangent of x, and cotangent of pi over 2 minus x equals tangent of x. So the idea here is that someone did actually think about this. And this was not something that happened overnight, but now when you remember this construction here, you now can see why someone actually did some homework. Sine, cosine, secant, cosecant, tangent, cotangent, cofunctions, cofunction identities. And these are very useful, extremely useful. Physicists love to use the cofunction identities because things get shifted around, and we do shifts when we do graphs, but we weren't thinking this way. We were just thinking unit circle, and now we're thinking, okay, well, this kind of gives us that transformation process that we were thinking about before. So we see that the sine curve is just a transformation of the cosine curve. Here, so we've got new ways of looking at these graphs vis-a-vis the transformation process. So we just keep generating stuff that's useful. And the more stuff we have, it does maybe make it a little bit harder, but it's going to make your process simpler if you can just kind of negotiate which will be the easiest. But if you take the longer route, that's okay. A correct route is always a good route. So what I want to do here are do a couple of identities. So when we prove an identity, we just show that one side equals the other. And that just means by whatever methods you like. So here, let's do this particular example. We want to prove, in this case, that 1 plus tangent squared of u divided by 1 minus, and again, these are just right from your WebAssign and right from your textbook, 1 minus tangent squared of u equals 1 divided by cosine squared u minus sine squared u. Now, some are really simple, and that's okay, but these are just basically set up to provide some work with identities. And so this is really kind of icing on the cake, so to speak. The only thing that we've added that's new are these ideas, and they're very simple. So we're just going to use what we already know. So when we actually do a proof, ladies and gentlemen, kind of like what I did up here, even though I'm not going to need a triangle, what I'm going to do is just transform one side into the other, and you can pick either side you like. So I'm going to start with the left-hand side. So left-hand side, I'm just going to go ahead and rewrite the tangent squared, even though in our minds we know that tangent squared is sine squared over cosine squared. But to make this a little bit easier, I'm just going to write it this way. Sine squared u cosine squared, and then 1 minus sine squared cosine squared. Now that's the left-hand side starting here, just making the definition of tangent as sine over cosine. So what I think I'm going to do to make this a lot simpler is just multiply and divide by cosine squared. So now I'm just going to do some algebra here. So if you like, you can write this in another color. Cosine squared divided by cosine squared, which is just, as I call that, a convenient 1. That's a common technique that we use in mathematics. So I'm going to multiply by 1, but that's going to be convenient. So now when I multiply by cosine squared in the numerator, I get cosine squared. But then, of course, the cosine squared is absorbed here, and I just get a sine squared. Here, I'll do the same thing. I'll get a cosine squared. And then the cosine squared is absorbed, and I get minus sine squared. So this is pretty easy. Now we know cosine squared plus sine squared is the fundamental identity. That's just one. So we get cosine squared u minus sine squared. And this is the right-hand side. So the technique is basically to transform one side into the other, and you can pick either side. There's no right way or wrong way to do a identity proof. I mean, when you prove formulas in mathematics, you use whatever is at your disposal. With Heron's formula, I didn't tell you what the formula was. We just derived one. So sometimes it's better just to say, well, come up with a formula using semi-perimeter. So here, this is just basically an algebraic manifestation utilizing the identities that we already know. That's it. I will say these will come in very handy. So put these on a note card and practice writing them down. Draw your triangle and just practice. Now let's look at another identity. That was pretty easy. So let's try this one. So let's look at, here, let me get a new sheet of paper. So we want to prove the following identity. Here's another example using what we already know. So prove, now remember what's an identity? An equation that is true for all values of the variables for which it is defined. So don't worry about division by zero. We don't care about that. We're not talking about that. So this is a break from all the arithmetic of the unit circle. So this is easy. Everybody thinks that the calculations are simple. They're the most difficult because that means you really do have to know what you're doing. So let me actually write this correctly. We're going to have 1 plus sine x divided by 1 minus sine x minus 1 minus sine x divided by 1 plus sine x. So basically, when you look at this, you reciprocate this and put a minus. And we are led to believe that this is 4 times the tangent of x times the secant of x. Now, when you look at this, and then of course, the main thing you do is you start to do a problem, you just check and double check that you've written it down correctly. The sad reality is that if you have a typo in the identity, then it may be very hard to prove, and you may spend a lot of time. Maybe you end up proving a new identity. That would be lucky if just that one typo actually created something correct, but usually it's nonsense. So be careful, and I'll be careful also. So with our proof, let's just go ahead and start with the left-hand side and do some algebra. Since it's a little bit more complicated, I think we can get farther down the road with the left-hand side. So the left-hand side, if we look at this, the first thing that stands out is just getting a common denominator. So the left-hand side will just be 1 minus sine x times 1 plus sine x, just a common denominator, like adding 3/5 and 2/3, or subtracting them. So now here, we're going to have a 1 plus sine x times 1 plus sine x. So that's 1 plus sine x quantity squared. Here we're subtracting, and we're multiplying 1 minus sine x times 1 minus sine x. So very simple. That's why we did all the stuff with the Heron's formula and the law of cosines, to get you back into the routine of doing algebra. And it hopefully is helping. So now, at this point, we're thinking, okay, well, downstairs we have a difference of 2 squares, which we can rewrite just like we did with Heron's formula proof. And here we can expand these binomials. So we have 1 plus 2 sine x plus sine squared. And then we have minus 1 minus 2 sine x plus sine squared, using parentheses, of course. And then now, let me try this. I'll use a touch screen. There we go. So let's see here. There we go, that looks a little better. And then downstairs, we've got what? 1 minus sine squared. And you always think about where you're heading as to how to shape your algebra. So now if we look up here, we have the 1 minus the 1, so they absorb, so these absorb. And then we have the sine squared minus the sine squared, so the sine squareds absorb too. But notice with the minus here, we get the sum, we get 2 sine x, 2 sine x, so that's good, that's going to give us a 4. So this gives us 4 sine x. And then, of course, 1 minus sine squared is the Pythagorean identity, cosine squared. Now, of course, equal opportunity. Let's just divide up the cosine. So we get 4 times sine over cosine times 1 over cosine. But of course, this is just the tangent and this is the secant. So indeed, we get 4 tangent x, secant x, which is the right-hand side. And we're done. So again, this is just an academic exercise. Now you're thinking, do you do this in mathematics? Well, absolutely. There'll be times when you're doing derivations and you'll have to manipulate things in a way to rewrite expressions. Maybe we're trying to solve an equation, ladies and gentlemen, and we got all kinds of trig functions and we need one. So we've got to use those trig identities to rewrite the equation so we can actually solve it. So there, for instance, you're not going to use identities every time you do a math problem, but there'll be instances where you're going to be forced to manipulate equations and expressions so that you can analyze them using the techniques that you actually know. So absolutely, this is an important process. Now, let's just look at another one. I've got several here, and then we can just do some basic simplifications. So here's one here. Let me again give a little extra space on the page. So let's prove this. This one looks kind of interesting. That kind of the same. Let's try this one. So here we want to prove that cosine theta divided by 1 minus sine theta. This is kind of fun. I enjoy this lecture because the Heron's formula and the trig identities are fun, a nice change. So maybe you enjoy it, maybe you don't. I hope that there's some relief. So this says that where this is defined, it is true that cosine divided by 1 minus sine theta is equal to secant theta plus tangent theta. Now, one thing about identities that's kind of interesting here is that it's not always obvious. I mean, you know, when you work with identities, you don't just stare at it and say, oh, well, I think that's true. Well, you have to work it out. And if you use the identity a lot, then it becomes second nature. You know, like, you know, 1 plus tangent squared is secant squared. We use that all the time. That's something that we've got up here. You know, but again, it's very basic, but something we use all the time. Now, this one might not be something we see a lot, but we still can do the transformation process. So in our proof, let's do this. Let's just start with this side so I can introduce a new technique to you, or actually reintroduce a technique. So the left-hand side is just cosine theta. It's just basically the convenient one. So what we can do, this is called the conjugate technique, where we're thinking we can transform this if we introduce the difference of 2 squares. So we're going to multiply by the conjugate of the denominator, just like we think about complex conjugate with imaginary numbers. 1 plus sine theta. A common trick that you will use often, and use often in calculus. So we can think of this, you know, just go ahead and put in some parentheses if you like, so you know that we expand this correctly. So now we have our convenient 1, and then we have what? Cosine times or plus cosine times sine. So when we multiply, we get cosine theta plus cosine theta times sine theta. And then, of course, downstairs, same song and dance, 1 minus sine squared. You can always start doing an identity one way and then change it up, but that's okay. There's no unique way to do this, and I'm not saying that this is the best way, it's just a way to do it. So now you can think, all right, well, if we have this, let's make it even smaller and replace this with cosine squared. So we have cosine theta plus cosine theta times sine theta. Of course, we can factor that, but let's have a reason to factor it, right? So this is cosine squared here. So now you're thinking, okay, let's go ahead and factor the cosine upstairs to retire one of the factors of cosine in the denominator. So we have cosine theta times 1 plus sine theta divided by cosine squared theta. So of course now we can absorb this cosine into one of these factors, and this will give us 1 plus sine theta divided by cosine theta. And of course now we just break up the fraction, so we get 1 over cosine theta plus sine theta over cosine theta. And so now, of course, this is secant plus tangent. Which is the right-hand side. So again, there's no right way or wrong way to prove an identity. In the WebAssign, they might have like some blanks, and they'll start to set up the proof, and you fill in the details. It's kind of like basically a computer algebra proof where you write it out, you look at what they're doing, you write it out, then you go back and you fill in the blanks. So that way you can be tested on the proofs, the identities with the computer algebra system to back you up. Now, of course, when you look at it, you're like, well, I don't think I would have done it that way. But, you know, stretch a little bit and think about, okay, well, if I actually started with this side, I'd need to do this. And so the WebAssign will guide you, but you can go ahead and work it out and then compare. And then if you need to make modifications, you can. Now, another thing that we want to be able to do when it comes to the identities is you're thinking, you know, is there any use for this in calculus? And of course, the answer is yes. And you will learn a technique in calculus 2 called trigonometric substitution. So I want to give you an example of where we could actually use our knowledge of trigonometry to do a rewrite of an expression that's algebraic. So this is kind of going backwards. We've used the inverse trig functions to rewrite a composition where the inner function was inverse trig, so we could write a triangle and then work the problem backwards and give a nice algebraic expression. Now we're going to go in the forward direction. So in this example here, I'm going to simplify this, but we don't really need to simplify it. Let's see, I'm going to have the absolute value of secant. So I'll just say this. I'm just going to say that in this case, theta lives, and you're going to see why I say this, lives between negative pi over 2 and pi over 2. Now, when you look at that, you're thinking, oh, Professor Ron, that's the range of the inverse tangent function. Okay. So just look at this, range of inverse tangent function. So maybe we want to see where we can use some of this. I'm always alluding to the calculus, but really all of this algebra we're doing is actually going to help you in calculus because you're going to be doing that uh, every day of the class, just like we're doing here and more. Now, here's something that may be of use to you. So for instance, consider this algebraic expression that has a radical in it. So consider this expression, 1 divided by x squared times the square root of 4 plus x squared, right there. Now, what's going to happen is that you're going to be asked to integrate this in calculus 2. So you're thinking, okay, all right, so that might be kind of daunting. You're thinking maybe I can use integration by parts. And I'm like, well, I don't think that's going to work too well. And that doesn't fit any form unless you're going to be working with inverse hyperbolics. And so the idea here is that when you see certain forms that remind you of the Pythagorean radical, you think trigonometry. Okay, so here's what we're going to do here. So basically, here's what the problem would be in calculus. I'll just write it out. It would look like this. That would be the calculus problem. So here's the calculus problem. So how does trig help you solve this? Well, we're not going to do any calculus here, but we're going to rewrite what I initially wrote, the 1 over x squared times the radical. So we can use trigonometry to rewrite the expression in x. So, and I'm going to show you how to do it. And I'm going to show you the substitution we're going to make. So here's the expression. That's why Dr. Stewart's book is so good. And here's what we're going to do. We're going to say, let x be replaced with 2 tangent theta. Right there. Now, you know inverse trig. So if I divide by 2 and take the inverse tangent of both sides, we're good to go. Notice this says what? Tangent theta is x over 2. That defines a right triangle right there. We already know how to do that. And also, it defines the angle theta. We've done all of this in our homework. I'm not doing anything I haven't already taught you. This is easy. You know how to do this. This is inverse tangent of x over 2. So of course, theta will have to live between negative pi over 2 and pi over 2 based upon the inverse trig. So that's kind of where I started here. And so you're thinking, all right, well, this is a triangle. Let's draw the triangle. Let's just draw an associated triangle with this tangent function. Theta. Tangent theta is opposite over adjacent, x over 2. And then you're thinking, oh, look, Professor Ron, x squared plus 4 square root. There's the hypotenuse. Oh, I see why we did this. Boom, boom. So this is trigonometry. So when students get to this part of calculus 2 and they didn't pay attention in trigonometry, this is a nightmare. So this is what I'm talking about. Sleep now, pay for it later, and possibly fail. The idea is that the prerequisites to calculus form the linchpin of your success. Any weaknesses that you have in the prerequisites will show up in the calculus sequence. So it's better to retire all of those weaknesses now and be ready for calculus. I mean, I've had students who have done no work in the prerequisites get to me in a calculus class and think I'm just the worst person in the world because I actually expect them to be able to do trig. So don't find yourself in that situation. Don't find yourself where you blame someone else for your lack of success. Own your work now and learn it. So now you see that this kind of substitution will allow us to rewrite this. So let's do the rewrite. So now what we want to do is just fill this in. So x is 2 tangent theta. So let's write it down. So we're going to do 2 tangent theta. You're thinking we could do these separately and substitute them in, but let's just go ahead and do this as a calculation. And then I'll write the radical with the 1/2. So we have 4 plus 2 tangent theta quantity squared to the 1/2. Okay? So now, well, this is going to be 4 tangent squared. And now in the radical, this is what we need to do. That is, we're going to think, okay, well, let's go ahead and expand this. So we get 4 plus 4 tangent squared theta to the 1/2. And now it's like, okay, we can factor the 4 and then take the square root of that. So we have 4 tangent squared. This is side calculation. In Cal 2, this would be a side calculation, which you do quicker because you'd have more experience by then. So now we have 4 times 1 plus tangent squared. Now we've got the square root of a product, so that's the product of square roots. So the square root of 4 is 2. 2 times 4 is 8. And then we're left with, I'll write it in formal style, square root of 1 plus tangent squared. Now, of course, I'm filling in all the steps, making a little bit longer than we need to, but that's good. Focus that a little bit. Now, 1 plus tangent squared is our friend secant squared. So 8 tangent squared. So we have the square root of secant squared. Now in this particular trig substitution, we don't get a plus and minus, we can retire it. With the secant, not so good. Unfortunately, just, you know, math is not always perfect. You have to, if you do definite integrals, you have to figure out which branch you're using. So there's always arithmetic involved. Now, of course, the square root of secant squared is the absolute value of secant. So we're just killing this with all the steps. But now, the theta lies between, is in the 4th quadrant or the 1st quadrant where the secant is positive, x is positive. So we can just write secant here. So this gives us 1 over 8 tangent squared theta times secant theta. In this case, since theta lives in the 1st and 4th quadrants where the cosine of the secant is positive. So this particular transformation is actually user-friendly. And so now the only additional part that you'd have to do, so you would replace this in the integral with this expression and then write the differential. So in calculus, you'll learn how to write the differential of this. I'll just write it in for you, and you'll learn this in calculus. This is going to be 2 secant squared theta d theta. And so you're going to do what they call a miscellaneous substitution. You're going to replace dx with this, and you're going to replace the algebraic expression here with this. And then you have created what we call a trig integral. which you can do, which is doable. And then once you're done, you'll have all these trig functions and you'll use this triangle to go back to the original variable. So trig substitution is basically a technique using trigonometry. So when you start this problem, you're going to think, oh, I need to use a tangent theta, where a is here. A squared is 4, so a is 2. So boom, there's my trigonometric substitution. Write this, write the triangle, do the algebra. Here I've done a lot of extra steps. You'll be able to streamline some of this and then replace all of this in the integral and move forward with a simpler integral. So what we're seeing is that this is not a fix for every type of problem that you would do. The idea here is that when you have these Pythagorean radicals, the trig substitution as we have here is very, very convenient. Now, when the powers change, that's what you call elliptic integrals. And those, my friends, are complicated. You're like, okay, can't we go back to the Pythagorean radicals? So when you get into some of your engineering classes, you may encounter some elliptic integrals where you're going to need to do a little extra work. So that's why I tell my students in engineering, you're basically going to be doing advanced calculus, where you're doing more advanced integration techniques, which again require the same type of algebra, but an extension, so to speak. So what you're going to find in calculus is that some integrals are relatively straightforward, but other integrals are very, very complicated. But what you're going to do is find is that when you use this trig sub, you can generate integral formulas for tons of integrands with these similar features. And you can basically take an integral table and prove half of the formulas using trig sub, partial fractions, or integration by parts. Those are three very, very basic fundamental techniques that you're going to learn in your calculus sequence, and mainly in Cal 1 and Cal 2. And then, of course, in Cal 3, you'll deal with more vector analysis in 2 and 3 dimensional cases. So again, I want you to take this, and here's another thing that I want to share with you in closing. There are two other substitutions. So I want you to write these down and practice with them. So this is, we'll just go ahead and fill out the list. We'll call this the trig substitution. So we'll just go ahead and list the first one. If you have this kind of formula, number one, if you have the square root of a squared plus x squared, and just practice with these and figure out what this radical would be. In this case, we figured out that it was going to be sine, right? But you'll have to think about where the theta lives using the inverse trig function. So this is going to be x equals a tangent theta. A tangent theta. That's the substitution. The next one will look like this. Say you have, and you can use u squared if you want. It doesn't matter. U squared, a squared plus u squared. In integral tables, they lots of times like to use the letter u, but it's okay. Use either one. X squared minus a squared. So we're going to change it up a little bit. And this is going to mean you can use the trigonometric substitution x equal a secant theta. Now remember, in both of these cases, for the inverse tan, theta will live here, negative pi over 2 to pi over 2. And in this case, theta lives here, 0 to pi over 2, open, union, open, pi over 2 to pi. So that's kind of a thorn in your side right there. And then if you have this Pythagorean radical, where we have a squared minus x squared, you'll use the substitution x equal a sine theta. And then of course, in this case, theta lives here. Negative pi over 2 to pi over 2. So that's going to be similar to the inverse tangent. So you should practice on these. This is what we used in the problem right here. And then for these, see what these actual integrands or these radicals will be with these substitutions. So like we did here, we did this for this one, the first case. And then so when you get to Cal 2, you'll use these, you'll see these radicals and you'll use these substitutions. Again, it'll be like a trigonometry exercise in Calculus 2. You'll also use some of this in Cal 1, but this will be something you'll do in Cal 2. So this is kind of a preview of that. And basically why we can see, and if you like, go ahead and draw the triangles for these. You get the associated triangle and the associated inverse trig functions, which allow you to do all kinds of interpretations. So hopefully you've enjoyed what we've done today. This is good information. So what's going to come next, ladies and gentlemen, will be more identities. 7.2, 7.3 will be more identities. Then we'll do trig equations, which will be your favorite, Professor Ron's lemma. And then after that, there'll be see you later trigonometry, but the remaining sections will tax you. They will be difficult. So get ready for that. Now, remember, we won't have any class on Thursday, so you have time to rest and figure out a good testing time for test number 3. And then once you do that, upload your PDF of your work and then start getting busy. I'll upload some more sections for the following sections and get busy with those. So I appreciate your attendance today. I hope this was informative and maybe gave you a little break from the tedium we've been doing. Everybody have a good day and stay warm. Take care.
Have a good day, sir.
Thanks.
Thank you.
See you, everybody.
Have a good one.
You too.